morning class and welcome to our course on sustainable energy technology. In the previous class, we started our discussion on how to use hydrogen and recover the energy that that has been used that has been stored within hydrogen, either in compressed form or any other form. So one of the most efficient ways of utilizing hydrogen to generate electricity is through the fuel cell. Of course, you can also burn hydrogen and generate heat and convert that heat into electricity, and that is a very traditional way of generating electricity, which can be used in many combustion systems, power plants, or in case where you want to use the heat directly in industrial processes, you can have industrial burners or furnaces to do that as well. So hydrogen is a very useful energy storage material that can generate heat at very high temperatures, unlike most other energy storage materials that exist. So maybe molten salt to some extent can do that, but it is still stuck within the solar thermal system. So hydrogen is one of the portable energy storage materials that can be used to generate heat using from a renewable resource. So if hydrogen is generated renewably, transported to an industry where it is used as process heat, it's one of the few ways to create renewable thermal energy at high temperatures. Okay, this is very useful, for example, in iron smelting, metal smelting technologies, and several other sectors which are often called hard to abate sectors, primarily because it requires certain forms of energy which are hard to obtain from renewable resources. So hydrogen can be a key energy storage material that can do that. So that is an important part. We will not go into that here. Here we will discuss about electricity generation from hydrogen through one of a novel technologies we are introducing, which is the fuel cell. So fuel cell is a direct energy conversion device, as we discussed last time as well, because it is converting a fuel directly into electrical energy without going the thermal energy route. This is useful because that means it is not constrained by Carnot thermodynamic efficiency limits, and it can have very high theoretical efficiencies compared to heat engines. It is also has a quick start and stop possibility, which makes it very useful. It has no moving parts and hence is easy to install and maintain, and it typically works best with hydrogen. So it pairs very well with a hydrogen production, storage, transport, distribution system. The disadvantage is it generates very low voltages. So it's typically like a battery, it generates typically around 1 volt of potential per fuel cell system, and hence large power generation and delivery through fuel cell stacks is often difficult. It can be done. You can have multiple fuel cell stacks and then increase the voltage and by decreasing the current through certain transformer systems and do it, but it is somewhat difficult and a little bit expensive because of the low voltage potential of fuel cells, just like batteries are. But fuel cells combined with hydrogen is a viable energy storage option for many renewable electricity generation systems like solar, wind, etc., just like batteries are, just like pumped hydro storage are. Okay. Also, fuel cell systems are viable for transportation as well. A hydrogen-based transportation systems, particularly for heavy trucks, trains, etc., where the battery weight will be too prohibitive, they can use a hydrogen storage plus a fuel cell system to as a transportation electric transport system. Okay. So electric trains, for example, long distance electric trains can be run if it has an onboard hydrogen storage facility along with a fuel cell facility that can generate the electricity to run that train. So we will discuss that basic fuel cell operation by using a common type of cell called the alkaline fuel cell. Okay. So basically what is happening is what happens in the combustion process. Hydrogen reacting with oxygen, generating energy and producing water. The difference is in combustion that energy comes out as heat. Here it comes out as electricity. And how is this done? You have hydrogen at one end flowing, oxygen at other end flowing. Okay. This is the cathode, this is the anode. Remember, anode is the electron donor to the external circuit. Cathode is an electron acceptor from the external circuit. That's how we are defining the anode and cathode here. It's an alkaline fuel cell, so the electrolyte is an alkaline solution like potassium hydroxide. Okay, so the transport, the ionic transport here is OH minus transport from the cathode to the anode. Okay, now what is happening in the cathode reaction? In the cathode reaction, which is the positive electrode here, of course electrons are going this way, so this must be the positive electrode, this must be the negative electrode. So in the positive electrode, oxygen is reacting with the water to produce, and electrons coming from the external circuit to produce OH minus. So it is absorbing oxygen from this side, absorbing water from the aqueous electrolyte from this side, and producing and absorbing and getting electrons from the external circuit to produce 2 OH minus ions. Okay, hydroxyl ions. These hydroxyl ions are being transported from the cathode to the anode. Okay, and here in the anodic reaction, hydrogen is being absorbed by the anode and it's reacting with the OH minus ions coming through the electrolyte to produce water and the electrons that are being pushed to the external circuit. So this electron flow through the external circuit can be used to generate work by, say, putting a light bulb or any other electricity consuming device. Okay. So hydrogen is being absorbed and absorbed in the anode and reacting with hydroxyl ions to produce water and electrons. At the cathode, these electrons and water are combining with oxygen to produce the hydroxyl ions. Okay, and the total reaction is H2 plus half O2 going to H2O. All right, water consumed is being regenerated here. So you do not need extra water here. Actually, you are generating water of the system, so you need a way to take out the water. Basically, water is being taken out on this side. All right, so part of the water is coming out of this system. Hydrogen is going in, water is coming out, oxygen is going in, and electricity is coming out. Okay. So this is a typical operation of an alkaline fuel cell. Variations of this operation will be seen in the different cases. The total reaction will always be this one. Okay. Now, what is the maximum voltage that you can generate out of this? All right. So now the maximum voltage for a fuel cell, and this is similar to for a battery as well, which goes which uses very similar principles actually. Here the EMF is defined as negative of the Gibbs free energy of this reaction. So this reaction has something called a Gibbs free energy associated with it, which is basically a combination of the enthalpy change and the entropy change happening during this reaction. Okay. For those who do not know what Gibbs free energy is, don't worry about it. Others who have done thermodynamic courses will know what Gibbs free energy is, and it is usually the quantity that is used for chemical reactions. Okay. So this reaction, hydrogen plus oxygen going to water vapor, has a standard Gibbs free energy associated with it in terms of joules per mole. So it's still an unit of energy, which is why it's called a Gibbs free energy formation, joules per mole. Okay. This minus delta G naught, this value is given for different reactions. So for example, for H2 plus half O2 going to H2O, the negative of the Gibbs free energy in kilojoules per kilomole, which becomes joules per mole, is 236,100. Okay, so the Gibbs free energy is minus 236,100 per mole of joules per mole of the reactant hydrogen. Okay. F is the Faraday constant, which is 96,500 coulombs per mole, and Ne is the number of electrons taking part in the reaction. So if you look at the half cell, 2 moles of electrons are taking part in this reaction. Okay. So Ne is 2, F is 96500, and delta G naught is minus delta G naught is 236100. If you put all of this together, then you get the EMF or the maximum voltage generated within a fuel cell like the alkaline fuel cell discussed here, and it will be around 1.223 volts, okay, which is quite a low voltage, okay, and this is even before currents are running. As soon as, so this is the theoretical EMF. As soon as the current density, that is the amount of current flowing through the internal and the external circuit increases, there are losses associated with the internal ionic transport, other losses associated with the chemical reactions that are going on, irreversibilities associated with the chemical reactions. So all of these losses decreases the cell voltage that is actually obtainable in the external circuit from its theoretical limit. Okay. And usually we operate in this region, which is more or less linear. This is a non-linear decrease. Here is also a non-linear decrease. In between there is a linear region where the fuel cells typically operate, and here it's called ohmic polarization. Don't have to worry about this. We can discuss this if any of you are interested. There are several types of losses that are happening at from low to high current densities. Ohmic losses are basically just resistance losses due to ionic transport. Activation losses are primarily when the chemical reactions are too slow. The reverse reactions often happen enough, so there is losses due to the reverse reaction. And when the chemical reactions are happening too fast, there is saturation problems and irreversibility problems associated with the chemical reactions, fast chemical reactions, which generates losses in terms of heat. So this is the concentration polarization loss. Okay. Because of these low voltages, several cells are connected in series to increase the voltage to create a fuel cell stack. But this reduces the efficiency of the cells. Increasing current flow also reduces the efficiency due to losses in the system. So even though the theoretical efficiency of a single fuel cell can be very high, it can approach 100% even, okay, the actual efficiency of a fuel cell stack is still moderate. So typical fuel cell stacks have 40 to 50% efficiency values, though max theoretical efficiencies can be above 80% even, okay. So these are some of the typical reactions. The hydrogen oxygen is the most common, and this is the most preferred for a fuel cell, but you can also use carbon monoxide, methane, methanol, ethanol also in certain types of fuel cells, and here you have the individual reactions, what happens in those cases, corresponding Gibbs free energy values and the corresponding maximum voltage that you can get out of that system, okay. Now, Gibbs free energy kind of increases, but per kilomole of reactants. But remember that the reactant mole numbers, molecular weights are also increasing. Okay, so in kilojoules per kg, you will have very similar values actually. All right, so this joule per kilomole is somewhat misleading in that regard. Okay. Now the next question is, what are the various fuel cell types that are there? Okay, so there are many types of fuel cells. Some are good for some applications, some are better for other applications. Some are good with some types of fuels, some are good with other types of fuels. So the typical types of fuel cells are alkaline fuel cells, AFC, the one that we just discussed. Then you have the phosphoric acid fuel cells, which is called PAFC. Then molten carbonate fuel cell, MCFCs, solid oxide fuel cells, SOFCs, proton exchange membrane fuel cells, PEMFCs, PEM fuel cells. Okay. Direct methanol fuel cells, DMFCs, DM fuel cells. Okay. And we will discuss these major types of fuel cells with their advantages and disadvantages next. So the alkaline fuel cells we already discussed. Electrode materials can be non-porous precious metal, non-precious materials. So you do not need platinum, for example. Okay. Operating temperature is also reasonable, around 70 degrees, but can operate over a wide range, 23 to 250 degrees centigrade. Efficiencies can be as high as 60% even for a stack. However, it is easily poisoned by impurities in the gas streams. So it works with ultra pure hydrogen and oxygen streams. Air does not work, which is a huge problem. So you have to separate air and produce 99.99% pure oxygen and 99.99% pure hydrogen. There should be no carbon dioxide, carbon monoxide, or any of these things, which makes the operation difficult. You have to have a very high fidelity purification system, which increases the cost of the gases. So this is primarily for space applications. So when you need electricity in space, this is a good place to go to. Suppose you are generating, you are using some sort of solar PVs to generate electricity. You can use that electricity to generate hydrogen by electrolysis of water, and then this hydrogen can be used in fuel cell systems that are present in space applications. Very good, high efficiency, but works with ultra pure streams. Then you have phosphoric acid fuel cells. So here, as the name implies, instead of potassium hydroxide, it uses an acid, a phosphoric acid, H3PO4, if I remember correctly. And porous carbon electrodes and platinum are used as catalyst. The electrode is porous carbon electrodes, and platinum is used as a catalyst coating the electrodes, which makes the operation expensive. Operating temperature is around 200 degrees centigrade, so it is a heated fuel cell, and efficiency is around 40%. So efficiencies are low also. It's a mature technology, but is expensive and has high specific weight. So the weight requirement is also quite high because it is using carbon electrodes and platinum primarily. A liquid phosphoric acid electrode, and it has a high operating temperature and reasonably low efficiency as well. Then you have the molten carbonate fuel cell, MCFCs. So here again the nomenclature implies what type of electrolyte is being used. The electrolyte being used is a carbonate salt, a molten carbonate salt, sodium carbonate, lithium carbonate, etc. Okay. So use molten carbonate salt mixtures as electrolytes, can operate with multiple fuel types. So this is a very useful advantage that is not present in AFCs and PFCs. This can operate on fuel types other than hydrogen. Okay, can attain around 50 to 60% efficiency. However, high operating temperature of 650 degrees centigrade is required. So you need to keep the system heated up. High operating temperature of 650 degrees centigrade is required. Precious metal catalysts are not needed. So it is somewhat hard to maintain because of the high operating temperatures, but on the good side, you do not need precious metals as catalysts. And these are primarily used for large stationary power storage and generation systems, because otherwise you cannot have that heated environment to run these kinds of systems. So large stationary power storage and generation systems use MCFCs significantly. Okay. Then you have SOFCs, the solid oxide fuel cells. Here the solid oxide material, yttria stabilized zirconia, is used as electrolyte. Okay. So again you remember solid oxide battery technology. So this is similar, it's just the fuel cell is very similar to those kinds of systems. So the electrolyte is a solid oxide material, yttria stabilized zirconia, and it operates at even higher temperatures, 800 to 1000 degrees centigrade. Does not require precious metals and can operate with multiple fuel types. So again, those advantages are there. You are not using platinum, and you can run multiple fuel types. It's a stable and reliable operation. Okay. So the oxide material is a solid, so you do not have a significant problem with hot molten stuff going around. Okay. So it's a stable and reliable operation. Up to 60% efficiency is obtainable. Precious metal catalysts not needed. Okay, so we've already said this. high temperature can lead to certain issues. High temperature can lead to slow startup and material durability problems. So it is not a start-stop operation, because you need to reach up to the temperature and only then it gives you good efficiency. Okay. Similarly, after stopping, it needs to cool down before it can be restarted again. Okay. Is used for large to small stationary power generation as well as on some portable systems. Its primary purpose is stationary power generation, but recently some portable system applications of these SOFC fuel cells have also come into the fore. Then you have one of the most common types of fuel cells that are now being used in the industry. It is called a PEM fuel cells, PEM, proton exchange membrane fuel cells. Again, if you looked at the electrolysis case, so if you look at electrolysis, batteries, fuel cells, those are very similar to each other. So you have a solid oxide based electrolysis systems. The reverse of that is a fuel cell systems. Okay. Similarly, if you look further back, let me just go back a little bit. This solid oxide electrolyzer cell, okay, is basically a solid oxide fuel cell system run in reverse. There you are using electricity to generate hydrogen. SOFCs use hydrogen to generate electricity. So you can see the system's reversal in that case. Okay. Similarly, the PEM fuel cell is this PEM fuel cell here is basically the reverse of the PEM based water electrolysis system, where you are again using electrolysis in a PEM. What is PEM? It's basically a proton exchange membrane called naphion, and you are running that in reverse and you are generating electricity, whereas in a PEM based electrolyzer system you are using electricity to generate hydrogen. Okay. And there is significant similarity with battery technologies as well. So for many of the for example, the solid, the molten metal based batteries are very similar to the molten carbonate fuel cell systems. Okay. What is happening in a battery material is in the discharging process, the material is being consumed. Okay. Then you are recharging it back and the material is coming back. Here the material is continuously being consumed, material being hydrogen, and is generating electricity in the process. Okay. So these technologies are related to each other. They are using these half cell reactions to run their systems either in the forward direction or reverse direction, consuming electricity or generating electricity, as the case may be. Okay. So this PEM fuel cell is the reverse of the PEM electrolyzer system, contains a thin plastic polymer through which ions can pass. The membrane is coated on both sides with noble metal platinum catalyst particles. So this uses platinum catalysts. The membrane is typically a moist 0.1 millimeter thick naphion, sulfonated tetrafluoroethylene membrane, as we discussed, that can transport H plus ions. Okay. The electrodes are typically made of porous carbon. Okay, so these are you are having porous carbon electrodes which are coated with the platinum catalyst, which can help in the reaction processes, and the intermediate electrolyte is a polymer exchange membrane naphion, which can transport H plus ions. PEMFCs can operate at temperatures below 100 degrees centigrade, making it ideal for many applications where you cannot go to high temperatures because of thermal management and user difficulty issues. It has high power densities and low specific weights and volumes, which is very important. You get high power densities, you will get low specific weights and volumes. The usage of solid electrolyte also eliminates safety and corrosiveness concerns. So in one sense, it's very similar to a phosphoric acid fuel cell system, but you are not using a phosphoric acid. Okay, you are using a moist naphion based membrane, which is a solid moist system. So there are no corrosiveness issues or no durability issues associated. Okay. They also have fast start and stop capability, easier thermal management, and are more durable. Okay. The usage of solid electrolyte also eliminates safety and corrosiveness concerns associated with liquid electrolytes, as we discussed. Hence, PEMFCs are suitable for light duty operations, portable power systems, and vehicle engine technologies. So when you are looking at fuel cell vehicles, which is also a technology under development in many places, this is the type of fuel cell that is being used. Okay. However, usage of noble catalysts increases the cost and a reasonably pure hydrogen stream is needed. Okay, so you do not need as pure as an alkaline fuel cell condition, but a reasonably pure H2 stream is needed for this to work, because the electrodes and the platinum catalysts specifically can get poisoned by carbon monoxide, sulfur and other things. So that is a problem. Another variant of this is high temperature PEMs. So high temperature PEMFCs operate at 200 degrees centigrade and uses a mineral acid instead of water to moisten the polymer membrane electrolyte. So here the polymer membrane electrolyte is moistened by water. Okay. In this case, it is moistened by a mineral acid. These systems are more tolerant to carbon monoxide impurities in the hydrogen stream. And also the increasing the 200 degrees centigrade also means that its efficiencies are typically higher. So this kind of a system can be used for a stationary electricity storage systems. Okay. The final one is the direct methanol fuel cell. As the name says, it can use methanol, CH3OS, the smallest alcohol type, directly. In the other types of fuel cells, you can use carbon monoxide for some cases like SOFC systems. Some cases can use methane as well. This one can use methanol directly. Okay. It's a variant of the PEMFC only, where a platinum ruthenium catalyst is used on the anode side, which can extract H plus ions directly from methanol. So it's a variant of PEM fuel cell, but instead of a platinum catalyst, it uses a platinum ruthenium catalyst, which works well to extract H plus ions from methanol, so that an upstream hydrogen generation system is not needed. Okay. It operates between 60 degrees and 130 degrees in light duty and portable applications. So suppose you are converting hydrogen into methanol, which is a reasonably good hydrogen storage material as well. It's a liquid system, it has high density, so you can convert it to methanol reasonably easily and use this methanol in your fuel cell, then DMFC is the way to go. Okay. So these are some of the types of fuel cells we discussed. We will in the next class we will have a brief one. We'll discuss the principle of all of these fuel cells, discuss the advantages and disadvantages, and then finally close the hydrogen part of our class. Thank you for listening and see you in the next class. Thank you.